Yeah, I was gonna say this is insane and there's different. I'll say that the information. I don't think we need to, quite frankly.
Wow. It's just like, I think sometimes I feel like even the directors, you know, it was just a joke.
Like, yeah.
But now the buddies want to go to chair park because we're just like
You seen the first?
no.
That's probably better.
I think it's just a bunch of guys trash word. Good.
Well, certain, yes, certain, yeah. Hard.
I thought you mean that just like screwed around.
Yeah.
Like we were in there and there's like there's supposed to be nobody, but then there's like three couples. You're trying to like so they have to do with like going loans and like engineering, you know, it's supposed to be smart people. I'm going to there was an ad with some lady saying, and I was like, boys, I don't think that's real. We started losing our mind, but the couples were learning that. It's like, bro.
Last night I got together. I used to watch the 1982 thing. It's a great movie. Yeah, it's fantastic. Not one for slandering. Well, yeah, like. Sure, what is? Yes. You know, you want to know fun fact? Complex numbers are called complex because they don't understand.
Alex had a really funny way of memorizing the stuff. And I was trying to remember it.
Boring astronomers. You could go get it. Gratification.
No,
Boring astronomers. I can't remember either, but it had something to do with old people. What is it? I know. Remember what Worm said?
I remember
But he made it.
I didn't hear him say, but they didn't really want
to. So much already proven. 22, because most of the time it's like, you know, sometimes they'll say something totally like out of line. Like when he was standing back the first time, like,
all right. I hope you all had a good weekend. So let's get started. The first thing I wanted to point out, in case you didn't already know, is that assignment number 3 is on the course website. So that will be due a week from today. And you should be able to complete that assignment after we're going to introduce one final thing about complex numbers. And then once we've done that, we'll move on to a new topic and you'll be set for getting started on assignment 3. So let me just remind you of what we know so far. Really, the only things that we've made use of about complex numbers is that we could represent them in 2 different ways. One is in sort of like a component form, x plus jy, where x is the real component and y is the imaginary component. Or we could represent it as a magnitude, a length, and an angle phi measured from the real axis. And so we represented that as z, absolute value of z times e to the j phi. We had a way to go between these 2 different representations. So if I give you the magnitude and the phase, these shouldn't be thetas, they should be phi's. Right here, we want these to be phi. So if I give you the magnitude and the phase, you can calculate x and y. Or if I give you x and y, you can calculate the magnitude and the phase. Yeah. Oh, sorry, did you have your hand up? Oh, no, sorry. Okay. So we're only going to define one more thing, and it won't take long. It is the complex conjugate, and it's denoted by z star. And the definition for taking the complex conjugate is, regardless if you're going to represent your complex number in component form or in this kind of more like a polar form, all you have to do is wherever you see a j, you replace it with minus j, and that's the conjugate. So if z is equal to x plus jy, which is equivalent to the magnitude of z times e to the j phi, then z star, or the complex conjugate of z, is x minus jy, which is the same thing as the magnitude of z times e to the minus j phi. So all we've done is replace all j's with minus j. So it's the same thing. Like if someone had given you an x minus jy or something like that, and you want to take the complex conjugate, you just reverse the sign in front of j. So whether you have a minus j or a plus j, when you take the conjugate, you just reverse the sign. So we reverse the sign in front of all j's when taking the complex conjugate. So, I mean, that's fine for a definition, but why would we want to do this? Let's consider the following. So I'll make myself. So let's consider the product of z and its conjugate. Okay, well, let's calculate it in 2 different ways. So we could say if we have component form, z is going to be x plus jy, and then z star is going to be x minus jy. Okay, well, let's just do the multiplication, right? So we're going to get x times x. It's going to be an x squared. Then we have x times minus jy. So that's minus jxy. And then we have jy times x. So our other cross term, so it's plus jxy. And then we're going to have minus j squared y squared. Okay, so we go minus j squared y squared. Okay, and so you can probably see already that we have a minus xy with a j, and we have a plus xy with a j. But those things are just going to cancel. And this minus j squared is the same thing as minus 1 or plus 1. And so all we're left with is the sum of x squared plus y squared. But what is x squared plus y squared? If we go look back here, yeah, it's the magnitude of z squared. So this is just z squared. And so therefore, z times z star gives us the square of the magnitude of z. So this is the square of the magnitude, or if you like, the length of z. Do we have something analogous for, like, how would, if I had a vector v, how would I find the length of that vector? Or the square of the length of that vector? Quadrature sum, but how do you get to that quadrature sum? Let's see, finding the length of, let's say we have vector v is some vx component in the x direction plus vy in the y direction. How do I find the square of the length of v? Dot product. So I'm going to take v. So the length of v squared is v dot v, which, as someone already said, is just going to lead to the quadrature sum of the two terms. And so for our complex numbers, z times its complex conjugate is sort of analogous to the dot product of real valued functions. Okay, so we can find the length or the square of the length of z by multiplying it by its complex conjugate. Let's try the other representation. So what about z times z star, where we write z in that kind of polar form where we have a magnitude times e to the j phi, and then z star would be the magnitude e to the j phi, except we have to change the sign in front of the j so that this is z and this is z star. And now we have an exponential times another exponential where it's just the negative of the argument. And so these are going to multiply to give a 1. And then you have z times z magnitude. And so this is the magnitude of z squared. So we get the same result whether we work in our component representation or our kind of polar representation. So that's good. That's consistent. So I want to show you one other thing that's useful about the complex conjugate. So another use for the complex conjugate. And that use is going to be to remove j's from the denominator of a fraction. So let's see, what do I mean by that? Let's consider the following. Let's take z is going to be the ratio of two complex numbers, z1 and z2. So we'll assume that z we want to write as x plus jy. And let's assume, so we want to find x plus jy. Specifically, we want x and y, given that, let's say z1, what variables did I use? z1 is going to be s plus jt, and z2 is u plus jv. So this s, t, u, and v, they're just numbers like 1, 2, minus 6, 17, stuff like that. So all I'm going to do is I'm going to just start by saying Z is just the ratio of these two. And so let's just see what happens. So therefore, Z is Z1, which is S plus JT, divided by Z2, which is U plus JV. All right. So I want to find X and Y for Z is equal to X plus JY. But the problem is I've got this kind of J in the denominator that's not allowing me to separate this into terms that have only real numbers and terms that involve J. So I want to get this J out of the denominator. So we want to remove J from the denominator. Denominator. Okay, good. The trick is that we're going to take the denominator, we're going to find its complex conjugate, and then we're going to multiply the top and bottom of our fraction by that complex conjugate. And what that's going to do for us is we know that u plus jv times its conjugate is just going to end up being u squared plus v squared. And so there'll be no j's in the denominator, and we'll have some product of stuff in the numerator that we can maybe manipulate. So let's see how that works. So Z2 is equal to u plus jv. That means Z2 star is equal to u minus vj. So yeah, minus j times v. So we want to multiply the top and bottom of our fraction by Z2 star, the conjugate. Okay, so let's see what happens if we do that. So Z is equal to S plus JT divided by U plus JV. That's just our starting point. Now we set the conjugate of the denominator. It's just going to have the sign of the J reversed. So I'm going to multiply by the bottom by that conjugate, and I'll multiply the top by that same conjugate. So essentially, I'm just multiplying this by 1, which leaves the ratio unchanged. But it's going to be convenient for us because we're going to get u squared, we're going to get a plus v squared, and the cross terms are going to cancel. And it'll always be the case that when you take a complex number and multiply it by its conjugate, those cross terms will always cancel. And so we'll end up with, in the denominator, u squared plus v squared. And so now that's sort of one of our main goals, was to get rid of the j in the denominator, and we've done that. So now we just have to multiply out the numerator. And so that's going to be what? S times u. And then what I'm going to do, I'm going to multiply these ones together first. J times t minus j times v is going to be a minus j squared t times v. I'm going to separate out these terms. We still have some more stuff to put in here, so we'd be a plus 1. Okay, let's do j t times u. So it's plus j t u. And then it's going to be s times minus j times v. So what was that? Minus j s times v. Okay, good. One thing we could do is we could say minus j squared is just going to be a 1, right? In fact, it'll be a plus 1. The j squared gives us -1, cancels that minus sign that we have sitting there. Okay, so that means z, which we want to express as x plus jy. What do we have left? SU minus TV. So SU minus TV. And then we'll go plus J. And now we have TU minus SV. TU minus SV. TU minus SV. Okay, good. And then it's all divided by the same denominator, u squared plus v squared. And so there we go. Now we have x is equal to the real component, which is SU minus TV over u squared plus v squared. And y is the stuff that multiplies the j, TU minus SV divided by u squared plus v squared. All right, and so there is our final results where we started with a ratio of 2 complex numbers, did some manipulations to, sorry, this is wrong, isn't it? What did I need a plus. Is that what you were gonna say? Yeah, you're exactly right. This is a plus.
You got it right.
This is plus. Yeah. There we go. Good. Any other mistakes? I think that's probably correct. All right. So complex conjugate can be used to find the magnitude of a complex number and to remove j's from the denominator of some kind of fraction of complex numbers. And so that's what it's useful for. All right. Good. Any questions? All right. So what I want to do today with the rest of the time is I want to get ready for the lab that you're going to do on Thursday. And we're going to introduce a device called the operational amplifier. And these are most commonly just referred to as op-amps. And what we're going to find is that op-amps are really quite nice devices because we can use them to design a lot of practical circuits that do useful things for us without too much effort. So for example, you know, the word amplifier, as it suggests, we can use op-amps to amplify signals. So if we have a weak signal that we need to make larger so that we can process it, we can amplify it by some gain. We can also do other interesting things. So for example, we can use an op-amp to add 2 voltages together. So if I had 2 voltages, like a sine wave and then some constant, I could add the 2 so that I get a sine wave that's offset from 0. We could do subtraction. We could also use an op-amp circuit to take a derivative of some voltage as a function of time, or we could integrate. If we can integrate, then we could use op-amps to build little circuits that solve differential equations for us. And so there's a whole variety of lots of things we can do. So what I want to do is I want to introduce the kind of fundamental characteristics, and then we'll very quickly start designing circuits with it. Let me draw you what it looks like. The circuit symbol for an op-amp is this little triangular thing. And what an op-amp has are 2 inputs. So an op-amp has 2 inputs. And I'm going to label these V minus and V plus. And we'll see why fairly shortly. So let me just label those as V minus and V plus. It has 1 output. And so I'll call that V out. So I guess we could be explicit. This is our output. The two inputs have names. The one with a minus sign is called an inverting input. And the one with a plus sign is called the non-inverting input. And usually on your op-amp, the inverting input will be labeled with a minus sign and the non-inverting input with a plus sign. The only other thing we have to draw here is the op-amp is a device that requires power. And so we need to connect it to some external voltage supplies. And usually those are drawn coming off the side of the device. And this, we're going to say, is plus VCC, and this is minus VCC. The CC is just conventional kind of notation. All it's going to be is a constant DC power, one of them positive, one of them negative. So what we have are two power terminals. And so we've got our positive power. This is typically plus 15 volts. And then we have our negative power. And so this is typically minus 15 volts. Okay, so when we're working with these op-amps, which you'll do on Thursday, we're also going to need some power supplies that provide the plus minus 15 volts. So we'll have a power supply as well. Okay, so let me just make a couple of notes. Often, students who are just beginning to work with op-amps get confused with these minus and plus subscripts on the inverting and non-inverting inputs. Those don't mean that this has to be a negative voltage and this has to be a positive voltage. So the signals we put into our op-amp could be negative or positive, or they could be something as a function of time that is sometimes negative, sometimes positive. So let's just emphasize that the two inputs, V minus and V plus, can each be positive or negative voltages. Okay, what else do we need to make note of? Okay, well, maybe for now, that's all we'll make note of. The way the op-amp is designed is that its output is determined by the two inputs, right? And so that's probably not a surprise. The output is designed such that it will be equal to the difference of the two inputs times some gain factor. We're not going to be concerned with how an op-amp is constructed. That's a little bit beyond what we're prepared to do right now. So we're going to treat it as a black box that's been designed to perform a certain function for us. So we will treat the op-amp as a black box device that performs the following function. Okay, so what it's going to do is it's going to take the two inputs, it's going to take the difference of them, so it's V plus minus V minus, times something that I'm going to call AOL. It's not American Online. It is an open loop gain is what this AOL represents. So OL is open loop, and we'll see what that means in a second. So this is called the open loop gain. All right. For the op-amp that we're going to use, the open loop gain is Well, the open loop gain is always designed to be very large. For the device we're going to use, it's about 200,000 or something like that. So we will use the LM741 op amp in the lab. And it is designed to have an open loop gain of about 2 times, well, here I'll say AOL is something like 2 times 10 to the 5. All right, I won't write it down, but we can also see why we have called these the non-inverting and inverting inputs. Let's imagine that I put in some small positive voltage on the V plus terminal, and I keep V minus equal to 0. Then the output is going to be some small positive number times a big gain. So we'll get a big positive number at the output. The output voltage would be the same sign as V plus. So that's why it's called non-inverting. On the other hand, if I set V plus equal to 0 and put a small positive voltage on V minus, the output will be minus the small number times the big gain. So we'll get a large negative value at the output. So in that way, putting a negative signal on positive signal on V minus leads to a negative output, which is the inverting part of it. Yeah.
So the way we obtain the value that you're going to the gain value multiply or whatever is entirely essentially arbitrary. You can figure out whatever method you want to derive this gain, correct?
Yeah, we can't derive this because we're treating the op amp as a black box, but there are a series of transistors in there where we can set what we want that gain to be. For us, really all we're going to care about is that this is really large. Because, you know, if this difference turns out to be a millivolt, 10 to the minus 3, and this is 10 to the 5, then that's saying we're going to get 100 volts at this output. And we're never going to work with 100 volts. But so it's just that this is extremely large will turn out to be important for us. And we'll see why. Okay. All right. The other thing that we should be aware of is in circuit diagrams, the power terminals, the plus minus VCC, are often omitted. The power terminals, plus minus VCC, are often omitted from diagrams. And that's just to keep your diagrams uncluttered. But we just have to know that even if they're not explicitly drawn, the op amp always needs to be powered in order to function properly. So the op amp always needs to be powered to function properly. Okay, so that means in a circuit diagram with an op amp, we might draw something like this. Here's our inverting input. Here's our non-inverting input. Here's our output. And with the circuit in this configuration, the output would be equal to the open loop gain times the difference between the voltages at the inputs. Okay, and so I haven't drawn the power terminals, plus VCC and minus VCC, but we know that the thing needs to be powered if it's going to function. Okay, so what do we need to know about the design of an op amp? So there are some limitations. the first limitation is the following. What do you think? Like, if I power this with plus minus 15 volts, what would you guess is the biggest possible output that I could get?
15 volts.
15 volts. What would you guess would be the smallest, the lowest possible output that I could get? Minus 15 volts, right? And you'd be pretty close if you guessed that. Inside this device, there's going to be lots of components and things like that. And so you don't get the full 15 volts. It turns out that you get about plus minus 14. So the first limitation is that the absolute value of the output has to be less than or equal to a saturation voltage. So this is a saturation voltage. And that saturation voltage is approximately equal to VCC minus 1. And so if we use VCC is equal to 15 volts, then V saturation is about 14 volts. So if we go back to that example that we were just thinking about, where we make this difference a millivolt, which is a small difference, right? A millivolt times 10 to the 5 means that we expect to get 100 volts here. We're not going to get 100 volts. We're going to saturate at 14 volts. If this difference was minus a millivolt, we would saturate at minus 14 volts. Yeah.
So that's due to the loss of taking that 15 volts and the op amp does something with it, and then you lose some at the end.
Yeah. The other design feature of the op amp is that the resistance looking into the device is very large. And so let me write it down and we'll draw a picture and then we'll see what that means. So the input, I guess we can start using impedance now, since we're familiar with the term. Or if you want, you can think of it as a resistance of the op amp is very large. This could be something like 10 to the 9 to 10 to the 15 ohms. So they're really huge resistances. Okay, so let me draw that picture again. So here's our op amp. Here's our inverting input. And here's our non-inverting input. And then this is our output. The out is here. Okay, and so what I'm going to do is I'm going to try to represent like an input resistance here. R in, let's say this is somewhere like 10 to the 9 to 10 to the 15 ohms or something, some huge number. And so now here's our inverting input and our non-inverting inputs sit there. So what I want to imagine is like, in principle, we could have some currents coming into or out of the op-amp inputs. So I'll label them as I minus for the current in the inverting input, and then I plus in the non-inverting input. But if these currents run into a huge resistance as soon as they enter the op-amp, then, I is like some voltage divided by R. And if we make R massive, those currents are very, very small. And the approximation we're going to make is that there is no current going into or out of the op-amp inputs. So we're going to say this has to be 0. So we will assume that R in goes to infinity such that I minus is equal to I plus is equal to 0. So no current flows into or out of the op-amp inputs. So there's another point of confusion here. This is absolutely true, and we'll almost always assume this, if not always. But we notice we did not say there is no current into or out of the output. So that's not true. So let's just emphasize that we can have current coming into or out of the output. Note, the output can have a non-zero current. Okay, good. So what we're going to do next is we're going to write down the so-called golden rules for op-amp analysis. And these are two rules where if we follow them carefully, make designing the circuits that I talked about, amplifiers, summing circuits, circuits that take derivatives and integrals, they are all going to be derived based off of these two golden rules. So op-amp golden rules. Okay. All right. So number one. Number one is really just related to what we just wrote down. I'm just going to repeat what I said already. Op-amp input impedance goes to infinity. And that means that I minus is equal to I plus is equal to 0. Okay, so we already had that one. But we'll just write it down again as a way of emphasizing that. Okay, the second golden rule applies only in a certain situation, but that situation arises frequently. So the second op-amp golden rule applies to op-amp circuits using what we're going to call negative feedback. And so let me draw what I mean by negative feedback. We're going to have our op-amp with the inverting and non-inverting input, and we'll have these two inputs, V minus and V plus. We'll have our output over here, V out. So that's our standard little circuit here. So let's just think about feedback for a second. Like if you were at a kind of noisy concert and you have some guitar player that's playing an electric guitar, so it's got some pickups. And what the pickups do is they sense kind of the motion of the strings, right? The pickups are little magnets, and then if you vibrate your string in front of that magnet, you have changing flux through a coil that's wrapped around the magnet in the pickup, and that induces a voltage which gets amplified and you hear it. So let's imagine you got this person playing an electric guitar, and they go right up to the kind of, I don't know, the amplifier. And now the sound coming from that speaker, it's a pressure vibration. And that pressure causes the string to oscillate a little more. And when the string oscillates a little more, the flux through that pickup coil, it changes more rapid. It changes more extremely. And so now you get a larger voltage that gets amplified back to the speaker, and it's louder. And that just runs away. That process runs away. And then you hear the squealing, that feedback noise that you hear from, I don't know, rock music. So the same thing can happen if you're just singing at a microphone. So you sing in a microphone, you have I guess singers have these monitors so that they can hear themselves. And if the sound from that speaker gets back into the microphone, then you get that runaway process again. That's positive feedback, okay? Negative feedback is what we're going to do is we're going to take the inverting input and we're going to connect it directly to the output. So this is negative feedback. Remember, this output is proportional to sum open loop gain times V plus minus V minus. So if I had, let's imagine that I connected this to the positive input, the non-inverting input. So I have a wire going from here to here, but not this one. Then that feedback is going to take a large output, feed it back into this input, gets larger, gets amplified again. That's the same process that we just described with the kind of noisy feedback at a concert. With negative feedback, however, we're going to take this output and let's say it grows a little bit, gets a little bit bigger. Then I come back here and I got a little bit bigger signal on this inverting input. That means this difference is going to get a little more negative. And so it's going to pull the output back down. And so the process doesn't run away. So that's why negative feedback, that's why that's the one we like. Okay, so what we're going to do is we're just going to analyze this case for negative feedback and see what happens. Okay, so we know that V out is equal to A open loop, V plus minus V minus, right? We've written that down 3 or 4 times already. Well, if I look at this figure that I've got, the output is connected directly to V minus using a wire with nothing in between them, no components in that. So that means the voltage at this node is exactly equal to the voltage at that node at the output. So with negative feedback, we will require the following. We require that V out is equal to V minus. Okay, well, fair enough. Then what we're going to do is we're just going to say this is V out, and it must be equal to this V out. So that means V minus is equal to A open loop, V plus minus V minus. All right, what I want to do is I want to solve for V minus. I've got V minus on both sides of this equation. I'm just going to rearrange it so that they're all on one side. Okay, so let's see. V minus. What are we going to have? We're going to have A open loop times V minus with a negative sign. We're going to bring that to the other side. So when I bring it to the other side, we get a plus V minus times A open loop. And what's left over on the other side is V plus times A open loop. And so that means V minus, let's see, A open loop plus 1 is equal to A open loop V plus. And so therefore, solving for V minus, we can write it as A open loop over A open loop plus 1 times V plus. All right. What is this fraction equal to? If A open loop is a huge number. It's 1, right? It's a number that's extremely close to 1, but just slightly less than 1. But it's so close that we're just going to make the approximation that what's in the brackets is essentially 1. If A open loop is really, really big, which is always the case, then V minus must be equal to V plus. And this is the second golden rule. Second golden rule. And we just need to keep in mind that there's a qualifier. And the qualifier is that this is true when you have negative feedback. So this is only true when using negative feedback. Okay, but as you'll see, as we go through the examples, almost all of the applications of op-amps that we look at will be using negative feedback. So what I'm going to do is I'm going to draw you the circuit that we're going to study in lab number 4, and then we'll analyze it. We'll complete the analysis of it on Wednesday. So first, op-amp application. So the application that we're going to think about, let me just emphasize that this is what we're going to be doing. Did I say lab 4? I don't know if I said that. We're doing lab 5 on Thursday. Okay, so it's an inverting amplifier. So we're going to make an amplifier. The goal of an amplifier is to take a small input voltage and to output a scaled up version of that, a larger scaled up version of that input. So what's it going to look like? We're going to have our op-amp here. Here's the inverting input and the non-inverting input. Here's our output. I'll just draw the output over here. Okay, what we're going to do is we are going to take the non-inverting input, which we call V+, and it's just going to be connected to ground. So we're putting 0 volts into this non-inverting input. Okay, and here this is also ground, and we'll measure our output between the output terminal and the 0 volts of the ground. Okay, so we still have our inverting input, and what I'll do is I'll connect a resistor to that inverting input and a function generator. This function generator will provide some kind of voltage that I'm going to call V in, and this is going to be resistance R1. Okay, what we don't have yet is our negative feedback, and that's what we're going to put in now. This time, however, I won't have a direct connection from the inverting input to the output. I'll make that connection through a resistor R2. Nevertheless, this is still our negative feedback loop. Okay, so we have 2 minutes left, and so we're not going to solve this today, but let me label this as V-. Let's just answer a couple of questions. Let's suppose that I had a current I1 going through resistor R1, and it comes up to this junction. What's going to happen at this junction? Is the current going to split, or or if not, what's it going to do? It shouldn't split because we said that any current here, say I minus, has to be 0. So it's not going to split at that junction. In fact, what's going to happen is it'll go up through R2. And in fact, what I'll do is I'm not going to call that I1, because that would sort of suggest that that's the current in R1. It is, but it's also going to be the current in R2. All right. What's the voltage at the non-inverting input? It's connected to ground. So this is at 0. Okay. So what's the voltage at the inverting input? Based off of this golden rule. 0, okay? And so that's absolutely true. And with those two things done, those are our golden rules. First golden rule tells us that the current in R1 and R2 are the same, and the voltages here are the same. They're both 0 in this case. And now that's enough where we could analyze the circuit and we could show that this output is going to be equal to the input times some gain factor, and we'll work out that gain factor on Wednesday. Okay, so we'll repeat the application of the golden rules that we've just done, but then after we've done that, we'll go on and finish the analysis of the circuit. All right, thank you very much, and we will see you in a couple of days. Yeah. Okay, just a sec. Yeah, just 1 second.